Okay, so for these three-phase generator problems, I said if you see one of these and I see the word generator, then I know that on the equation sheet, I'm going to be dealing with three-phase generator. In fact, inside of here is almost everything you need to know, with the only difference being these P out. There's multiple ways to solve for it, and you need to know efficiency is P out over P in. So knowing that, let's just start by writing what we know in this problem. Right here is the number of poles. So that may relate to our omega, or it may relate to our RPM. Here's Hertz, that's F. 450V, and this is the line voltage, right? Line voltage. It doesn't say that, but that's pretty much what we're always given. And that's because in the real world, that's what you can actually easily measure versus openings in your generator and measuring its phase voltage. You can measure the line-to-line voltage pretty easily. It's rated to supply 1687.5 kVA. So that is S. And we know that that is S because this is volts amps, right? And so that it doesn't say apparent power, but that's what this is. And I'll put the bars on it because that's apparent power is the magnitude of complex power. So this is S, and this is S total, or you could also say S of the three phases. And that's because that's just what it's supplying. It's supplying this total power. It doesn't say to a single phase. It is the total that all three phases can supply. And then here we have 0.8 as a power factor. So that's FP equals 0.8. And lagging means it's inductive, which also makes sense because that's almost all loads are inductive loads. And we put in capacitor banks to correct the power factor. Well, this one isn't fully corrected. It's not at unity. It's at 0.8. So if the machine was operating at rated conditions, what would be the real power and the reactive power and the current being supplied? So the only thing I'll add to this is P total and Q total, because that's what it's asking about. And then the current being supplied would just be current is I. And we could call this I line, or as Ashley pointed out, we could call it IA. It's still the armature, but in all of our generator problems, it says I line. So we don't call it IA in the generator problems because the line current is what we usually are measuring and dealing with. So that's the first one. The next one is if we were given an efficiency, then what torque? That's T torque. And if we look at the equation sheet, where is torque on it? It's only in one spot, torque in. That's the only torque inside of these generator problems. So in this one, we're going to find the T in, right? So what torque does the prime mover provide? Prime mover being whatever's making it spin. The hydroelectric dam, the wind turbine, the gas engine. So what is the speed of the rotor in RPM? And that's just RPM on the equation sheet. Right here, RPM, but it's actually NP, so we could also write NP. NP equals RPM, right? And that's what we're solving for, right? It's units in RPM. So the first one, if it's operating with these conditions, what would be the real and reactive powers? Well, we know S, we know the power factor is 0.8, right? S is 1687.5. Power factor is 0.8. That's cosine theta. So if I solve for theta, then I do cosine -1, 0.8, and I get 36.87 degrees. So this is apparent power S. If I just put the angle on it, it becomes complex power, right? 36.87. And then my favorite tip in the whole class is without even solving for anything mathematically, it's just a notational difference of polar to rectangular in the calculator, right? And if I go from polar to rectangular, I get 1350 plus 1012.5 J. This is the P in watts. P in watts. This is the Q in VAR. And note, whenever I did this angle, this is a positive angle and this is positive because it's inductive. It said it was a lagging. Lagging means inductive. This means inductive. And that works out. Here's a positive, which means the Q is also inductive. So there's the first two parts of what we're being asked to solve for. The next one would be the current. So if I'm looking at the equation sheet, here's where it gets a little messy, but P out equals √3 V line I line cosine theta, right in here. Well, we actually know all of these parts. Let's just write down that formula. P out equals √3 V line I line cosine theta. And so what we're asked to find is I line. So if we have I line, we can take that P out, divide it by √3 V line cosine theta. The P out that we had was right here, 1350. That was the P total, right? All three phases here, all three phases there, 1350. √3 V line was given, 450. And the cosine theta was actually the 0.8. So you could rewrite cosine 36.87, or you could just write 0.8 right here. And actually, I don't even have that solved. 1350 divided by √3 times 450 times 0.8, and I get 2.16. And that would be kiloamps because this was kVA, right? That's kVA. This was actually kilowatts, and this was kVAR. There we go. All right, I'm going to clear this so we can solve for the next part. So the next one that we're asked to find, we found the P, we found the Q, we found the current. If the generator has an efficiency, what torque? So we're solving for the torque in. Well, what equation relates to that is the power in equals torque in times omega. Do we have, let me look at mine real quick. Efficiency. Yeah, so do we have P out at 1350. Efficiency is 0.95, also 95%. So efficiency P out over P in. We can rearrange to solve for P in. This is one that people often mess up. They'll multiply the efficiency times the P out instead of dividing the P out by the efficiency. So I usually rewrite it just to make sure I don't make that mistake. But the other thing you could do is you could do like a sanity check of that your P in should always be greater than your P out because it's going to have some losses along the way. So here's 1421 kilowatts is the P in. Do we know the omega? We don't, but we can solve for omega right there. There's omega, here's omega. So I can solve for omega 2 poles 2 pi f. 2 over poles 2 pi f. Omega equals 2 over the number of poles 2 pi f. 2 poles was 4. 2 pi 60. 0.5 times 2 pi times 60 gives me 188.5. That would be radians per second if you needed it. And now for the T in, I can just do P in divided by omega, 1421 kilowatts over 188.5. and I get 7.54 kilonewton meters. There's my Tn. And the last step, what is the speed of the rotor in RPM? RPM, speed of the rotor in P, 120 equal 120 F over poles. And you could have actually solved this one as the very first thing because we haven't solved for anything for that. That's just taking what we knew initially of the poles and the frequency, right? See that? 120 F divided by P. So in P equals 120 F divided by P, 120 times 60 divided by 4, 120 times 60 divided by 4, that's 60, equals 1800 RPM. So there's part B, and here's part C.